All right, today we are going to talk about the squeeze theorem. So first off, what is the squeeze theorem? The squeeze theorem just says that if my function lies in between two other functions, at least on the interval I care about, and I can find the limit of both outer functions, and those limits are equal, then the limit of our original function is the same value. In math writing, we say f of x lies between two other functions. Let's call them g of x and h of x. All right, our function f of x is in between there. Well, if I know the limit as x approaches some value of g of x is equal to the limit as x approaches that value of h of x, well then in order for f to be squeezed in between there, then the limit as x approaches c of f of x is that same value. Let's call it L. Because if it's squeezed in between there, if both of these outer ones are reaching L, then the inside part has to also reach L. So our first example, let g and h be the functions defined here. G of x is sine of pi over 2x plus 4, and h of x is negative 1/4 x cubed plus 3/4 x plus 9/2. If f is a function that is in between g and h on the interval negative 1 to 2, what is the limit as x approaches 1 of f of x? So x approaches 1 is inside of this interval. That's all that matters there. Let's find the limit as x approaches 1 of g of x. Well, it's a trig function, so I can use direct substitution. That's the sine of pi over 2 times 1 plus 4. Well, the sine of pi over 2 is 1, and 1 plus 4 is 5. Then I need the limit as x approaches 1 of h of x. It's a polynomial function, so I can just plug in and use direct substitution. Negative 1/4 times 1 cubed plus 3/4 times 1 plus 9/2, which is 1/2 plus 9/2, which is 5. All right, since those two limits are equal, then I know in order for f to be squeezed in between them, the limit as x approaches 1 of f of x is also 5. I don't know what function f of x is, but I know that that limit must be 5. All right, f, g, and h are functions defined here. F of x is 1 minus cosine of x over x squared. G of x is x squared times the sine of 1 over x. And h of x is the sine of x over x. All of these inequalities are true, all right, as long as x isn't 0. But which of them can be used with the squeeze theorem to find the limit as x approaches 0? In order for the squeeze theorem to work, the left side and the right side have to approach the same value. So what is the limit as x approaches 0 of 1/3 times 1 minus x squared? Well, that would be 1/3 times 1, which is 1/3. And the other side equals 1/2. Well, those two are not equal, so number 1 does not apply, the squeeze theorem. Number 2, well, if I take the limit as x approaches 0 of negative x squared, I get 0. And the limit as x approaches 0 of x squared, I also get 0. Since those limits are equal, I can find the limit of g of x, so number 2 does work out. And number 3, the limit as x approaches 0 of negative 1 over the absolute value of x. Well, that limit doesn't actually exist. Let's look at the graph to see what that limit would be, just to be sure. Oops. I could plug values in, but it's a little easier to just graph it. Whoops, negative 1 over absolute value of x. All right, as I approach 0, it approaches negative infinity from either side. So we'll say that, negative infinity. That limit does not exist, but the limit as x approaches 0 of positive 1 over the absolute value of x. Let's check that graph as well. All I did was delete the negative. And that one approaches positive infinity. Those limits are not equal, so the squeeze theorem does not apply. The only one that applies the squeeze theorem is option 2. All right, g and h are functions defined here. F is a function that is in between those. What is the limit as x approaches negative 1 of f of x? So we want the limit as x approaches negative 1 of g of x. And we'll use direct substitution there. So I get negative 1 plus 2 plus 3, which is 4. Then I need the limit as x approaches negative 1 of h of x. And again, we can use direct substitution. You may be saying, do we really have to do both of them? Yes, you do. So we get 1/2 minus 1 plus 13 over 2, which is 7 minus 1, which is 6. Those limits are not equal. So we actually cannot find the limit as x approaches negative 1 of f of x using the given information. We don't have enough information to actually solve this limit because the two outer limits are not equal. All right, g and h are defined here. F is in between them. What is the limit as x approaches negative 1 of f of x? Just like the others, we'll take the limit as x approaches negative 1 of g of x, which is sine of pi over 2 times negative 1 plus 2 plus 3, which is the sine of pi over 2, which is 1, plus 3 gives me 4. And then we need the limit as x approaches negative 1 of h of x, and we'll just use direct substitution again. All right, that one's a little longer. We've got positive 1/4 minus 3/2 plus 9/4 plus 3. And just for fun, because I don't feel like doing my mental math, I'm typing it in my calculator. I got 4. The two outside limits were equal, which means the limit as x approaches negative 1 of our inside function is also 4. The limit as x approaches 0 of x sine of 1 over x. Well, this one we have to use our brain power a little bit. We know that any sine function is between negative 1 and 1. So the sine of 1 over x is in between negative 1 and 1. If I multiply everything by x, I don't know if x is positive or negative though, so I'm going to use the absolute value of x to ensure that it's definitely positive. Because remember, with an inequality, if it's negative, we have to flip them all. So negative absolute value of x is less than or equal to the absolute value of x times sine of 1 over x is less than or equal to the absolute value of x. I just multiplied everything by the absolute value of x. That inequality is still true. Now, if I can get the limit as x approaches 0 of the negative absolute value of x, and the limit as x approaches 0 of positive absolute value of x, if those are the same value, then I know the limit of the inner part. Well, these use direct substitution, so they are both 0. So that means the limit as x approaches 0 of the absolute value of x times sine of 1 over x equals 0. The only difference here is that it could be positive or negative between our absolute value and our original function. Well, positive or negative 0 is still just 0. So that means our original function's limit is also 0. All right, now you are going to practice some.